Good morning to everyone from me as well. Thank you for joining today's workshop on SSbD practice, our established critical barriers and success cases. As Alex said, as a chemical engineer, we're working in Excelsis, the company organizing this workshop. Excelsis is a consulting company based here in Greece and has a lot of expertise in vendor organization, business development, and innovation management. So Alex is Dr. Alexandros, who will have the first session. We are really happy to have gathered today representatives from industry, from research, and from policy to share their views on how SSbD is actually working in real life, not only as a concept, but also as practically and how looking at how we try to apply, to test it, and sometimes we start with. So, as you know, this workshop, as Alexis mentioned, this is a satellite event of the Conference 2022 conference that Excelsis and MBPI are co-organizing. And actually, I want to thank MBPI for being our main sponsor for this workshop. Let me also highlight that we have support, as Alexis mentioned, from the EU for this the workshop. This is why we will have several representatives from EU projects during our third session. As you might have seen, this workshop is going to be recorded, and we have some participants online, so welcome to our online participants as well. Our agenda will cover three thematics from SSbD and regulatory aspects to industrial success cases and also current challenges. So let's start with the first session. And that is focusing on SSbD framework, policy, and regulatory readiness. So we give the agenda and start with Dr. Katraouzos. We are very happy to have you with us. Dr. Hellenic is a mining methodology and mechanical engineer and a retired officer of the European Commission. He has a vast academic and professional background, having graduated from the National Technical University of Athens and completed his PhD on the Imperial College of London. During his long career at the European Commission, he was responsible for European research in areas ranging from mining and metallurgy to recycling, construction, industrial safety, and nanosafety. Today, he will share his reflections on SSbD concept and practice, and as he calls it, he will give us some insights from the future.
Yeah, I literally read the book, but don't make historical similarities. The similarities stop here. Good morning, everyone. I'm very glad to see you here at this workshop. The idea is that I give you some insight and a clear message that strategy has to be done by yourselves now. There's no one on top to make the strategy. So fortunately, we have delivered platforms and structures and clusters and everything able to put down the strategy and the roadmaps. And the need for those will come up forward. But before I go, I need to say a very warm thank you for this invitation. I have this luxury maybe once or twice per year, inviting me to give a short speech in a workshop. And hopefully some from the audience will pick up the message. We don't need everybody to get every message, but some people may get it. After these first words, let's go immediately into the subject, the hard matter. Safe and sustainable by design. Let's make, before we go in there, a preliminary remark. I have no slides, but don't worry, I will give you the conclusions. They are not many. I'll give you one by one, so you can note them down. First preliminary remark, we are here with the cutting edge of technology for safety, which means that if previous requirements like presence of regulation, like implementation of regulation, like laboratories able to detect the adherence to the law. And if all this does not exist, then maybe leave this for the future and deal first with this basis, rule of law, regulation. So conclusion number one, after maybe half a minute of speech, conclusion number one, where are we in a sector, in a country, in an area, in a scientific objective? So knowing where we are is a must. Safe by design is applied to new technologies mainly, new constructions, new technologies that are still in design phase. And these technologies replace other technologies which are already safe. So when the society replaces safe technologies, they need to make sure that the new ones will be an improvement. Now, these present safe technologies were innovations some time ago, because did not fall from the sky. We made it. Take any risk, take structural risk, take fire risk, electricity risk, whatever. So we made it with different methods and different data and different people and different assumptions and so on. So we have to deal with the societal requirement of better safety always, a risk aversion, we don't want risk that we don't know, and new risks are not easily accepted unless there is a direct benefit, and then people just don't care. You have all a mobile phone now. So you know this, the situation. So conclusion, the safety level is a moving target. You are shooting a moving target. The moment you approach it, it's farther away. So conclusion number two, don't take short-term goals. By the time you finish the research to achieve the goal, you are outdated. Go for the solution to the problem immediately, the real one. Then we come to the question, how much safety? What is safe enough? And there have been several approaches to answer this question. And one of them was, what is really the value of life? How much money do we need to spend in order to save one human life? But the approaches, especially an American judge did in the 90s, Tarpin, you may look it up, ranged from $10,000 in case of road safety to 200 million, some insecticides. So it did not come out well, this method. So we need to take a different approach that does not go that way. And that different approach is possibly, we don't know, a question to the society itself, because every safety investment means that you put their resources that you can use otherwise in order to improve the future situation instead of today's pleasure. In other words, how much do I invest, say, for earthquake risk? We know precisely what is the risk. We know how often we have an earthquake, what is the peak crowd acceleration. We know perfectly the spectral response of the structure. We have computers to simulate everything. We have shaking capes. We know perfectly. We know the steel more than our pocket We know the cement, the beton. We don't know that much the degradation over time because it ranges, but we know this perfectly. But if I ask you a question, how much this society wishes to pay for future safety in earthquake risk, then you will get an entirely different response in Japan than in Greece or in Armenia or wherever in the United States. So then, looking back, do we know what society wants to invest? Conclusion there, 3 therefore, social sciences must be integrated in the research from the start. Because this question, I don't know how else to answer. And we are not talking about today's society. We're talking about a society when your research is going to be finished. Okay, suppose these 3 conclusions have been received a satisfactory answer, then what do we do? What have we done until now? First remark is that we have waited for the damage first. We have waited for the risk to happen, not the risk, the hazard to happen. And then we investigate, and then we regulate. And those that do not submit themselves to the regulation, they are kicked out of the market. This is best explained in the case of materials by the European Parliament. Doctrine, no data, no market. So we have to have the product, we have to put it in use, even in test phase, it's equal, it's use, see what the effects is, and then we decide. Does this work? It's very simple. Huh? You have an authority, make a file, you send the file to the authority may say, okay, I can decide, or maybe I need more data, you send more data, say, okay, may I decide, finally it ends somewhere, even in the restrictive use, that this material is used for this purpose, but not for the other purpose. Or glyphosate may be used by a professional, but not by an amateur. In my garden, I cannot use it. I have to ask a professional to come to my garden and then put it, which is it real safety? But anyway, the trouble is that this does not work, because in order to clean up the backload of chemicals over the years, we're going to reach 2,200. And on top of that, we have about 3,000 to 5,000 new chemicals per year, which means fines, permits, and so on and so on. And worse, these materials are tested one by one. What about those which have additive effects, like some endocrine disruptors or other things? So completely different materials, but the same toxicity endpoint. Allergies? We don't know. So conclusion number 4, safe by design is not an option. You do it or you don't. You have no other choice. We have no other choice. We have to go that way. And other sectors have done it. I mentioned civil engineering. Why not the materials? You may say it's extremely difficult. But let's see, what is it? System by design means that once somebody gives you the safety level, you cannot decide by yourself. I hear very often the government say, I must ask the scientist what is the safety level. It's not the scientists who decide the safety level, it's the governments, elected people, they decide what we want. Once this safety level is given to you, then science can answer what method can be used and what is the cost of that method. So find the best solution on the resources that are that can be put in a structure or material or combination of materials or whatever, so that the predefined safety level is reached, which means that we need to know the system, the mechanisms which lead from the method that you choose, the technology that you choose, to the end toxicity endpoints. Now, this mechanism is not always there. I mentioned structural safety, but I mean, in the 16th century, we had no models of structural safety. Or I said earlier, we know perfectly still, but do we? I mean, even now, the car makers, they have to test each roll, steel roll, individually. Do I have time? Okay, 2 minutes, just enough for the sustainable. Okay, but the absence of mechanism should not be an obstacle. Maybe the possibility that we have to store and exploit big data can lead us to some conclusions of this question without necessarily knowing the mechanisms. How do we do that? The answer is always the same, both in safety and sustainability, is governance. That means governance has 4 levels. First is information, saying what you do and listen to what others do. Communication, say what you are going to do next. In the information is, of course, all the databases, all the models, all the things that allow you to study the problem. Communication, feedback. That's very important, the feedback. The feedback, and here is the reference to the title, is, have I done this in the past? And what were the results then? Not necessarily in the same field, in another field, another sector, or another issue. And if I do the same in the future, what will be my feedback then? So this is a study of what has this given in the past and what is going to give us in the future. So reversing this, can we dream for materials the same thing that we have achieved for structural safety, for example? Maybe 1 or 2 minutes, because entering sustainability, this means also the end of my conclusions. I don't have any conclusions on sustainability. I'll explain you why. First, sustainability is, of course, a further step, because safety is contained in sustainable. Non-safe is non-sustainable. That's clear. If we have a goal, we talked in length rather about the goals of safety that have been given to us by the society. But talking about goals in sustainability, that's entirely different, because a major issue here is the conflict between the goals. And then what are we precisely doing in sustainability? Do we have a progressing approach? So every time we make something new, for example, substitution of harmful chemicals. Okay, but I'm afraid that with the substitution, we just create the substitution needs in 10 years' time. PFAS is a good example. Do we go for disrupting? So go for the dream, for the feedback in the future, and let's work towards that mechanism for sustainability, so environment, economy, and so on. Third remark, sustainability is surely a global issue if some of our goals are of planetary level, concern of climate change or energy availability and so on. Do we have global governance? Can all the players? It does not make sense to try to solve a problem for one side and then on the other side you create bigger problems. Makes no sense. Then the obstacles to this road, several of them. First, supply of materials. I will not develop this, but it's a big issue. Why on earth did we develop batteries on lithium that we did not have? Either we had to develop lithium batteries and at the same time geology exploration for finding new lithium, or go directly for potassium. Potassium is only 5% less in reduction potential, so why not? Supply, man-made obstacles. The different regulations, the different marketing, the different levies and so on, taxes and all this stuff. Or maybe the open market situation. So we transport steel from the United States to Europe and from Europe to the United States, the same steel. Why do we do that? We do the same with, I don't know, cement and tomatoes. From one side of the earth to the other side of the earth. What's the point? Is this sustainable? The point is, of course, open market, regulation of prices. So market rules. Step backs. We have big events nowadays that get us back by a number of years. So how do we manage this? How do we continue that? In other words, but there is a positive matter that the governance model that we have established for nanomaterials, effluent fast materials and chemicals, not entirely, but okay, we are still busy, that can be copied and used for sustainability. So bringing the agents together, establish database, big data assessment, models, and so on, the exchange of experience from one country to the other, from one sector to the other. This can work. So that's a very positive conclusion. But I'm afraid that for sustainability, we have to step a little bit back and say, what are we there for the future? And then establish the roadmaps and then put in place the governance, all these contacts globally. And hopefully we can drive ahead. Remember that from the moment you start the strategic thinking until you have main routine practice is about 30 years. Thank you very much.
Thank you. I would like to welcome you all in today's workshop SSbD in practice, and especially our guests from other countries of European research area. I would like to say that our association has initially a positive approach towards SSbD. First, because it's a mind shift, as you also mentioned. Second, because we don't see it only as a regulatory requirement imposed by European authorities, but mainly a strategic opportunity to build confidence towards our customers, align innovation with societal and environmental needs. And this is why it fits perfectly SSbD with the strategic goals of our association, which we call in short HATSI, which are to reinforce international competitiveness of Greek chemical industry and further our footprint at European level. And this is something we have achieved in recent years because although the our European chemical industry has problems, the whole industry in Europe, Greece has made a remarkable turnaround. We have increased our export share, which shows in various destinations, which shows that Greek companies are indeed able to develop and offer marketable solutions worldwide. And we should not forget also that Greece is geographically speaking, the closest European state to big markets in third countries, in Asia and Eastern Africa, which is also an opportunity for the European trade surplus, because this is something challenging at the moment. At HATSI, we embraced SSbD soon enough through incorporating it to the national transition pathway towards 2050. This has been a comprehensive work addressed to the national authorities, but based on European framework. Mr. Bikos is here. We cooperated closely on guidelines like circularity, funding, human capital. This has been published in April 2024 to address to the Ministry of Development, where also the General Secretary of Research and Innovation belongs in Greek government. After that, we are very glad to see more practical progress. Enhanced cooperation, not just communication, between our companies and universities, institutes. And what is even more pleasant to see in practice are the success stories, the developments of many of our members, how they advance at TRL scale. And this will be also the key topic of thematic 2. I will moderate it later on, with 4 of our members showing what they have done, but also 2 prominent speakers from Italy, as I know. HATSI is active here also in thematic 1 with our Deputy General Director, Mr. Skarlatos. But I will stay till the end because I'm very interested to listen also to the presentations of thematic 3 about the projects, because as an association, we are also very well connected with CEFIC, the European Association. We would like to get also the negative feedback, so that you mentioned some obstacles. That's very important for us, how to push, because we advocate as well as an association, to push at national and also European level. So I would now prefer to give the word to the more experts. Thank you again. And I also encourage the open dialogue between all stakeholders here throughout the workshop. Thank you.
Thank you. Hello, good morning, everyone. Many thanks. Let me start from the important things. Many thanks to the organizers, especially Joanna and Alex, for inviting me, giving me an opportunity to come to Athens. I would pay to come, but actually I didn't have to. And many thanks to MDPI, who have been very kind to me in the organization of the previous event Alex just mentioned, and again invited me again to come here. So I'm very pleased to be here. How do I even start introducing SSbD, safe and sustainable by designs, and how do I bring the principles to this audience of experts? I will try and keep it very simple, a very broad oversight. I have lots of slides, but I will not talk details. I will just try and bring the principles, speak at a high level, and hopefully the rest of the day will hear a lot of the details. So let me see. So where did it all start? Well, it all started with the first speaker we had this morning. So the European Commission, as it was expressed or introduced to the scientific and industrial community through George Katraouzos, drove us all towards safe by design, as we heard earlier, and then later, more recently, towards safe and sustainable by design. So that's where we were before. Then, but why? I think George explained it all, but just to put his vision and oversight into small practical elements. There was a lot of European policies that still govern our activities, and I will mention just a few: the Green Deal, the zero pollution. We all heard them all. This is the actual driver towards SSbD, because it is embedded in European policy that we should do things safely and sustainably. And the word should is actually chosen to indicate that this is not law, it's not imposed. It's at this stage voluntary, but hopefully it makes sense, and hopefully it's the direction that we as, well, first of all, as citizens, and then as practitioners, as scientists, this is the way we choose to go. It's strange to talk about SSbD's early years because it's literally just a few years back. So we had Safe by Design. We started talking about, again, with George, maybe more than 10, probably 15 years ago. But safe and sustainable is really a more recent concept. And as George already beautifully explained, a far more complex one. So safe is perhaps a lot more of a black and white concept than sustainable, and a lot easier, I would argue, to predict, perhaps because we've done it for longer, perhaps because if something's not safe, it's quite straightforward. But sustainability changes. Sustainability changed in the last few weeks just because geopolitical things changed around the world, and that changes or that switches in just a flick or a part of an eyelid. So it can be a more complex system then to address when you're trying to be both safe and sustainable. But back to timing, 2022, we had the first safe and sustainable by design concept. The fundamental principles are listed here, but they're in a few just very simple words. The concept is that you cannot develop, or you should not develop, new materials, new processes, new chemicals independently of the potential safety and sustainability elements. So great innovation is fantastic, but if you are going to innovate amazing materials, chemicals, and then fail to bring them to the market because they're not safe and they're not sustainable, then why go through the process? Instead, the better way is to assess all these variables, functionality as well as safety and sustainability, right from the start. The JRC did produce a lot of documentation in the early days of SSbD, the 2022 framework, let's call it, and I will move to the more recent framework after that. So they provided guidance, they provided use case examples, and they worked with the community. They organized workshops and, of course, under the auspices of the European Commission, but they worked with the community to translate SSbD from a concept to something that could be worked on. So the key elements of the first SSbD framework were that, okay, we need, first of all, to assess hazards, so toxicity exposure. We also need, if we start talking about sustainability also, we also need to look into environmental impact. develop a life cycle thinking for materials and processes, so that it's not just static, but also we see something from its cradle to its grave. And I will go even beyond that eventually in my presentation. And of course, performance and functionality needs to be part of the whole deal, if you like. The key elements of the 2022 framework were well designed, well thought through, but as a prototype always is, there were issues. So it was very linear. It was it wasn't well defined simply because there was no data or evidence or worked cases to actually help us specify things with more accuracy, with more prediction, with more clarity. So, and of course, there's a question mark. Was it industry friendly? The informal words from industry was that we can't work with this. I was really glad to hear a previous speaker being so positive about industry's view on SSbD, and hopefully the new framework is something that we can all work with much, much better. So a few key elements. I've literally taken a few pictures from the first SSbD framework documentation just to help me make the points. And the key elements of the initial framework were that it was qualitative or semi-quantitative, and as I said, not perfectly worked through, and it was limited in terms of cases or where it was applied, and therefore other cases may not have been so easy to apply, and the concept of standardization was not there at that stage. The key elements, I think I've touched on this a bit earlier, but just to sort of focus again our minds, was hazard, working safety, environmental safety, sustainability, and there was the notion that this fifth step was the socioeconomic effects, which were very nebulous, and again, there was a lot of feedback that perhaps not too well described or not too well represented in terms of how would you apply socioeconomic principles in your assessment. So things moved on. Where are we now? In 2025 version of the SSbD framework, we're still talking about safety. Of course, we're talking about sustainability. Now we're also talking about circularity, which is, let's say that if before we would start from 0 and go to 320 degrees. Now we have to do the whole 360 and reach a circular concept in our SSbD assessment. And hopefully it's a lot more industry friendly. So what brought us to this new 2025 version of SSbD? There's been a lot of work. Some of the projects that did the groundwork we will hear about later today. So I do not want to do any spoilers, but these projects fed into the new SSbD framework. There was a lot of industrial participation, and that also helped. And there was a lot of effort, again, huge credit to the JIC to work with us and with all the use cases to turn it into a framework that might be better or easier to work on. And this is what the new framework looks like. So before we had a very linear structure, now we're talking about a more circular design of the framework. We're talking about a more structured, multi-step assessment with perhaps a key element of the new framework is this decision gate. So things go in a more structured way from one decision to another. And the safety, sustainability, and circularity are well integrated in this new framework. Oops, please forgive my slides were a little bit strange there. Okay, so the new framework appeared in just last year. In the last few months, we had a new methodological guidance. Of course, you probably all know about it, but if not, I would recommend that you take a good look of it, because a lot of new things have appeared there, including modeling, AI tools, ways to do things and to make them transparent. Again, I don't want to say too much, partly because we'll hear a lot more, and partly because of time. I mentioned stages and gating, and the stages are very clearly defined in this new framework. So we have the stage 0, which is a problem framing, which in a coating scenario would be the function of the coating, and then scoping, safety, sustainability, and so on and so forth. Just a summary slide of what the two frameworks, how the two frameworks differed, and I wouldn't call it even differences. I would call it an evolution from a first trial to a more defined, more well-structured guidance. And hopefully SSbD now can be something that people don't feel, especially industry, and ultimately it is for the industry, with our support from regulation and from academia, to deliver this SSbD framework in particular specific applications. And hopefully this is not seen as a burden anymore. That's the vision. It's not a burden, it is actually a benefit. Your products are better, they sell better, just to put it in very blunt terms, because they are SSbD compliant. Now, I want to say a few things about communities, because we wouldn't have got where we are with SSbD if there wasn't a lot of community supporting this this activity. And I will specifically say a few words about the NSC, which used to be called the Nano Safety Cluster. It's another one of George's babies, but now it's called the Network for Safety and Sustainability of Chemicals and Materials. Like everything else, like the SSbD concept, the NSC has also evolved. It's a more it has a new name, new direction, new participation. Many of the projects that we've been presented here are parts of the NSC community. I don't want to say too many words because I realize I'm out of time, but I want to emphasize how important it is for people to do things as communities, to work together rather than work individually, and that supports the whole process, and that is effectively a very safe and sustainable way of doing things. So just literally run through my slides about the NSC. You can see who we are in the picture. We organize events. We have lots of projects and initiatives. We keep track of our past projects, our present projects, and we also group in what we call sister projects. So projects funded under the same call are grouped as system groupings that work together, organize activities together, present themselves together. So not George will laugh because he remembers what we used to be like. So nobody talked to nobody else and everybody was doing their own stuff. Now I think we are a lot more harmonized as a community, and let's face it, we need to be also. I will just say a couple of words about how dynamic now the scientific community is, especially as part of the NSCs. So our working groups are not more static. We have a dedicated SSbD working group for the obvious reasons. We've moved into advanced materials again for the obvious reasons. I will also just mention literally in 2 seconds the IRIS SSbD community. That's another community that, in fact, Stelios will speak about a lot more later. So I'm saying nothing more other than to emphasize that we need to work together and use these communities as our springboards to push in the right direction for SSbD. And I think with that, I will thank you. And
hello, everyone. Thank you, Anna, for the invitation. My name is Katraouzos. I'm the Vice President of SSbD, and I'm the Deputy General Director of the Hellenic Association of Chemical Industries, also known as HACI. So, my expertise is in regulatory and sustainability compliance. This is through the consulting company SSbD. We're a technical consulting company that specializes in environmental affairs, in engineering, in manufacturing plant design, in regulatory compliance for all types of products, and on sustainability issues such as reporting, ESG, eco-design, etc. Very sensitive. Okay, so in my presentation, I will talk a bit about the interaction between safe and sustainable by design, as we used to know, as we know it now in 2026, and the legislation of products, the eco-design legislation of products, and the legislation of companies. These two are entwined, greatly entwined, and with a new framework that takes into account the latest EU policies, it is even better, greatly entwined, and that makes it, will be my conclusion, even more friendly for the industry. So, as Ms. Marcelini said already, we have a new framework that was published by JRC in 2025, and it was adopted by the Commission in 2026. It replaces the previous one. It makes it a lot better, in my own opinion, basically because it takes into account all the new policies that came out between 2022 and 2026. Such as the EU Competitiveness Compass, the Clean Industrial Deal, the Chemical Industry Action Plan, and of course, there are great many legislative frameworks that came out since, such as the Deforestation Regulation, the Carbon Border Adjustment Mechanism, and many other regulatory frameworks that, in my opinion, cooperate and work well with the SSbD principles. Really difficult to navigate this. Okay, so the new SSbD structure is more circular of sorts compared to the previous one. I will not analyze this because it's been already told. What I will say is that the safety and sustainability assessment step is still there, is still in place. It is greatly expanded to include socioeconomic factors, which we'll discuss a bit more in the presentation. And this is the major step of SSbD that interacts with the current EU legislation. So, in 2022, the safety and sustainability assessment had 4 major steps. The first 3 steps have to do with the hazard of the product itself, either the intrinsic properties or the process-related hazard or the final application of the product. And step 4 was basically the environmental sustainability, an LCA. It was basically an LCA. The new framework builds on that, switches a bit the titles, adds more criteria. We'll see more about those. And also on the sustainability part, adds the socioeconomic aspect. In my opinion, when the previous framework required someone to know, for example, if you wanted to implement SSbD in chemicals, what you needed to know, you need to know REACH, CLP, and LCAs. This, if you knew these legislations and methodologies well, you could do proper SSbD. Now this is not the case anymore. Now you need to know pretty much every legislation that it is out there in the European Union and everything that will come up in the next 10 years that will affect your product and the principles. The basic legislation that cooperates well with SSbD is the SPR, is the Eco Design and Sustainable Product Regulation. This is a regulation that came out in 2024. It has a huge scope. It affects all types of products except for food, feed, pharmaceuticals, vet pharmas, animals, and plants. But the trick here is that although it affects every product out there, from devices such as cars, fridges, whatever, to basic chemicals, it does not apply directly to any type of product. So what this regulation does is sets up the basic principles of how every legislation that will come after the publication of ESPR will be implemented throughout Europe. Either that would be detergents, fertilizers, packaging, waste management, or wastewater management, or whatever else. And these principles are basically three. There are some basic eco-design requirements. These are the categories that are described, which everyone must meet. There are performance requirements, which say that it does not only, you do not only have to meet a baseline, you have to go beyond. And if you go far beyond, you are rewarded. We see that with current legislation, like the packaging and packaging waste regulation, we'll discuss a bit more. And there is also information requirements. There has to be transparency, either through digital product passport or other means that will become available soon. Companies will have to demonstrate what they say is justified and it complies with the rules and regulations. Just to give an example, there is a specific criteria for chemicals that are the substance of concern. These are not a substance of very high concern, for those that are familiar with REACH. This is a different group of substances, which is a lot broader compared to the SBCs, to the substance of very high concern, these substances should be restricted depending on product type and product category in one way or another. They cannot be certified for eco-label, perhaps, or they have extra reporting requirements if they contain substance of concern. Just to give an example of one criteria of ESPR. So, how these two together work? The Safe and Sustainable by Design, the ESPR, and all other relevant EU legislation that currently or in the future will apply. As we saw earlier, SSbD practically has a different approach now than it used to have. There are not 4 steps, there are 5 steps. The step 1 is always the same. It is the intrinsic properties of chemicals and materials, how hazardous these materials are. And there are 3 criteria that are described currently, which describe these substances, split the substances into 3 possible categories. Category 1 criteria H1 is the very harmful substances, and the SBCs, the substances of very high concern. These substances are described by REACH, are substances that usually carcinogenic, mutagenic, or toxic to the reproduction system, or are really hazardous, like endocrine disruptors, or very mobile, very persistent, etc. These categories are described by REACH and by a communication of Commission in 2024 about the essential uses of chemicals. So, in order to identify the substances that fall in criterion H1, you need to know at least these 2. There are other legislation as well involved, but at least those 2. For the second criteria are the substances of concern, are the substances that I saw already earlier. They are described by Eco Design and Sustainable Product Regulation, the ESPR. They include very hazardous substances, but also some even less hazardous, like skin sensitizers, or some substances that are toxic to the environment. And there is the third criterion, which is basically every other hazardous substance out there. It can be something that is just irritant or causes some minor skin or damage or something. All these are described in the regulation CLP, the General Chemical Regulation about classification, labeling, and packaging. So as you see, when it comes to identifying what falls into what category according to SSbD, you need to know the main legislation about chemicals, how these are classified. When we say something is toxic, what we mean, how this is justified, and what it means for something to be toxic. Steps 2 and 3 pretty much remain the same when it comes to SSbD, but hasn't remained the same when it comes to EU legislation. So step 2 is mainly everything that has to do the production and the process, the occupational safety, the environmental safety through production and process. And step 3 is about the product itself, how this interacts with the users, the consumers, the professional users, industrial users, how it is, what is the end of life of the product, etc. These steps used to be part of the SSbD of 2022, but the European legislation have greatly changed. If you see in the list of legislation, you see that many of these legislations are from 2024, 2025, or even 2026. We have great many new legislation regarding the occupational safety, or many changes to current legislations. For example, REACH is a regulation about the occupational safety that has included new criteria when it comes to hazardous substances. We have new hazard categories. We have new restrictions about microplastics, for example, which is slowly being implemented. And of course, we cannot ignore the PFAS, which is also another REACH restriction that is coming soon. And also we have various new or updated regulations regarding industrial emissions, F-gases, pollutant substances, plastic pellet laws, etc. When it comes to the end product, the final product, depending on the product category, there are as well very different legislations that have been recently updated, most of them. There is a legislation, there is an overall legislation about the product safety, GPSR, General Product Safety Regulation, and then depending on what is the use of the product, there is a legislation that sets what's sustainable, what is safe, what to look for. It could be biocide, fertilizer, detergents, cosmetics, toys, electronic devices, even tobacco products, even specific aspects of these products, like its packaging, how it should be transported if it is hazardous, how it should be handled as a waste or later on as a wastewater, etc. So the legislation framework is even more complex, despite that the basic principle of SSbD pretty much has remained the same. It is more difficult to implement it now because of the legislation. Then we have the fourth step, which is basically the environmental sustainability assessment. What the SSbD requires is an LCA. It is a vital step. You cannot have a sustainable product without knowing what is its impact on the environment. This is beginning to be understood also by European legislation that requires from products to have some sort of LCA. SSbD suggests that companies use the product environmental footprint methodology, but this is very limited at the moment. Most companies do their own environmental footprint assessments or go with established criteria such as the EPDs. The life cycle assessment for the environmental sustainability assessment is a very good example. Like, companies usually are not required to do it now, but all the information that companies will get from performing an LCA will be useful to them in various regulatory compliance requirements. Construction products will be required soon to run their own LCAs, so whoever has done it already is a step ahead. Batteries will require to have their own LCAs. carbon border tax is calculated according to the LCA, etc. And the final step, the socioeconomic sustainability, which is entirely new to the SSbD, has been well defined with the newest SSbD. It is the most interesting of the criteria because they are relevant to also very new legislations in Europe. They are mainly connected with the sustainability reporting legislations, such as CSRD, SSbD, which affect the very big corporations, but also affect their supply chain. So even smaller corporations will be affected by it. So if you perform a social LCA as part of the SSbD, you will help yourself to achieve various regulatory requirements, or you will produce the relevant data that will be asked by your supplier or your client that has to do their own regulatory requirements, such as sustainability reported, critical raw materials, or even more wide regulations, such as the deforestation regulation. And to sum up, ESPR and SSbD are very different between each other, but they work together as well. ESPR is a regulatory framework. It is obligatory to the companies. It has principles that have to be implemented. These principles work well with SSbD. SSbD is already there. It's already suggesting many of these principles. They work well together. To end up to my final point, that is that if you perform for your products SSbD well and according to the current guidelines, it is almost certain that you will cover most, if not all, of your regulatory requirements. So as someone said before, this is a very industrial-friendly framework that adds added value to companies. They want to do it because it is a holistic approach to regulatory and sustainability compliance. And this is very great compared to the previous SSbD. So this was my presentation. Thank you very much for your time.
Good morning. Thank you for the invitation. I'm Marina Soufra, Marketing Manager at NEOTEX. Today, we'll try to present you how safe and sustainable by design can inspire us and how we use it as guidance into our product development process. Just a few words about NEOTEX. NEOTEX is one of the leading paint and construction product manufacturers in Greece. We operate 5 production units. Sustainability is not something new for us. It's a part of how we operate for many years. Since 2016, we have continuously sustainability reporting. We have initiatives for waste, use of green energy, photovoltaic panels, and of course, many product certification and TPDs. As I mentioned before, sustainability and safety in paint industry are addressed through multiple different frameworks and regulations. Each one of these certifications and regulations focus on different aspects. For example, hazard classification, emissions. In addition, there is a lack of harmonized standards for performance of paints. This situation creates problems for us. It's difficult to compare our products, to have a unified view of product sustainability, and make a decision, business decision. As referred before, a safe and sustainable by design framework includes safety assessment, environmental assessment, and socioeconomic assessment. These aspects are not independent and sometimes create important trade-offs. This is why it's important to use this concept in our product development process. In NEOTEX, we try to incorporate this strategy in 2 processes, in new product development and in our product portfolio evaluation. For the new products, We define early the function, the raw materials, the intended use in order to ensure safety and sustainability in the design phase. And for existing products, we try to find improvement opportunities and, of course, to have decisions, for example, formulation or phase out of existing products. Let's explain now how we translate these principles, safety, socioeconomic and environmental assessment, into practice. We start with safety. At VTEX, safety goes beyond compliance. We monitor continuously the regulatory updates, the substance of concern. We try to adapt our formulation early before changes become mandatory. So we follow a proactive strategy. Of course, we emphasize indoor air quality. It's very important to select raw materials with low VOC content. We follow strict control for VOC, for our products' VOC emissions and content. More than 30% of our total production consists of ultra-low VOC product with VOC content below 1 gram per liter. And of course, it's very important on designing products to take care about the safety for their intended use. Moving to environmental assessment, we integrate LCA from the design stage. It's very important to evaluate CO2 emissions and other environmental indicators early in order to select to have more informed selection of raw materials and formulation characteristics. More than 70% of our total production volume is already covered by LCA. Also, we emphasize on monitoring ESG indicators. We track key intensity metrics such as GHG emissions, carbon footprint, waste generation. During the recent years, we have measurable results and we have important reduction in these metrics. Furthermore, durability is very important for us. We integrate it in our equities and we follow a cradle-to-grave approach. To explain further our environmental approach, we follow, as safe and sustainable by design principle, the system described, a full life cycle. Most equities today are cradle-to-gate options, but we follow a different approach. We take into consideration also use phase. We consider the full lifetime of the building, using a 50 years period of the building lifetime in order to incorporate the repainting cycles required to maintain the performance over time. We use, of course, compliance methods, already established methodology like EN 15804 and PEF. We use the durability schemes from PEFCR for decorative paints in order to link durability with environmental performance. It's very important also to incorporate in our sustainability system socioeconomic aspects, life cycle cost, not only the cost during production, but also the cost regarding application and maintenance. We look at supply chain responsibility. We evaluate our suppliers, we prioritize the most compliant and reliable suppliers, and we monitor the risks related to regulatory updates and availability due to the current situations, of course. Also, we have metrics for our product profitability and competitiveness. It's very important to optimize performance and cost. To bring all these dimensions together and inspired by this framework, we have been working on pilot methodologies in 2024 to unify safety and sustainability. The first step was to select and integrate different metrics for environmental impact, performance values, socioeconomic parameters. And then we apply a structured scoring approach in order to have an outcome. This outcome is not just a number for us. We classify our products regarding their sustainability score, and then it helps us as a decision-making process to decide which products are already safe and sustainable, which products need to be reformulated, and which products maybe we have to phase out. So, to conclude, we use the principles and the concept of safe and sustainable by design in order to not find perfect solution, but to balance better between safety, sustainability, and business value. And it's not something new for us. It's a way to structure how we operate. Thank you very much.
Good morning to everyone. My name is Maddalena Rostagno. I'm the CEO of the company DG Advanced Automotive Company in Italy. I'm partner of the Mozart project, and I would like to thank Excelsis for this invitation and say hello to all of you, to all the friends and partners in Mozart. And I'm really sorry not to be present in person today. The presentation that I will illustrate you is about our experience with artificial intelligence to use in a more powerful way life cycle analysis for decision making in material selection for better sustainability. Few outlines about the presentations, a quick glimpse about who we are, which is the potential in using AI together with LCA for material and process selection. How we achieve that? It's through the application of unsupervised learning artificial intelligence algorithm and through generative AI for data manipulation. Where we started, we used the European life cycle dataset to make our research, our experimentations. And we applied to aggregated data that we elaborated the algorithm K-means. That is one of the most common and most used in unsupervised learning. Through that, we clusterize, compare, and make selection of materials for our applications. To start, a few information about who we are. We are a partner in automotive design and manufacturing of automotive companies. Our main products and services are related to material and process redesign, finalized to development of advanced components. We mainly deal up to now with the re-engineering of standard components with alternative materials and more productive processes. We carry out pre-industrial and mock-up testing. Of course, we are now experimenting with AI to improve our services through predictive modeling, digital twin, and of course, AI tools for improved material and process design. Our goal with this experimentation has been to explore if LCA as a tool can be used as a decision-making tool. We all know that in the market, as a consequence for many European research projects, many private investigations, there are plenty of LCA analyses that have been carried out. Unfortunately, this result has not been fully exploited from the industrial point of view, because in the most of cases, they remain there as an information, but they are not used to move forward. We saw that through the use of artificial intelligence, is it possible to extrapolate, filter patterns from the information that LCA is giving to have information about specific materials and processes for that specific applications that we need. This is what AI we saw can do. A quick look about the algorithm that we used to achieve this goal. Unsupervised learning fall under the category of machine learning, but in this case, we don't use labeled data. We do use data in which it's known that there are relationship dependency among data. We use data that have the equal weight. In technical terms, data that are unlabeled. And in this way, it's possible without prejudice, clusterize this data, group them, map them, and make comparison. That in material selection and in design, it's very useful. We choose the classic algorithm for our experimentation. It's the K-means clusterings. Very quickly, I will tell you that this is a choice is due to the fact that you can manipulate large data set. You need medium computational power, but above all, it's a fast algorithm that allows to have, a preliminary qualitative analysis. That it is what we need. Where we took our data sets for our experimentation. The problem is always the data sets. By luck, the European Commission had these very useful data sets. We downloaded them. The European life cycle data sets are publicly available. And the European Commission explicitly recommend their use for education, research, for policy making, and for presentation. So we were sure to don't have any confidentiality breach by using this data for our analysis. Unfortunately, they are uploaded in a compressed format. As you will see the Zolka, I'm messing up with the video, the Zolka format, for which it was necessary, before being able to implement them in our AI algorithm, it was necessary to manipulate these data sets when we download them, because they are distributed in Zolka format. I bring your attention to this workflow. And you can see that we started with this format. The Zolka format contains both compressed and metadata set, and a specific procedure for extraction has been needed and has been carried out through LLM, the use of large language models, and also through Python coding. In this way, it was possible to obtain a structured data set, finding missing value that always are there, normalizing the unity of measurements, and also harmonizing all the data. At this point, through LLM, we carried out a preliminary life cycle analysis that we know is not precise, but here, I repeat, we are doing a qualitative investigations about LCA, and we obtain for each of these files the impact categories. Then again, through Python, we convert these datasets in the CSV format. That is the most suitable one for artificial intelligence algorithm. And as I said, we apply in our case unsupervised algorithm, the k-means one. What we obtained? We realized that we were dealing with 99,000 files. Among them, after data extrapolation and manipulation, among them we found there were only 4,000, 6,000 unique processes. So it's very difficult to navigate through these data sets that are uploaded in this large repository. And above all, we saw that not for all these processes, all the 5 impact categories that we considered were available. It is in some cases was a difficulties, and it required a further filtering and cleaning step to retain only high quality, well-formed data entries. And at the end, we remained with these data sets for different material type, and we focused our attention on the data set related to metals and on the data set related to coatings. In these presentations, I will show you the results that we obtained for the metals datasets. Here we have the printing of the first 7 lines and the related impact categories that we obtained for the coatings dataset, in which there are 45 processes and materials with all the data necessary to calculate in proper way the impact categories. And in this slide, you see the results we obtained with the metals dataset. 91 processes, 91 different processes, and their impact categories. The LCA has been carried out through Python coding for the data manipulation and exploratory data analysis, and large language models for the calculations of the impact categories. Next step has been finally implement artificial intelligence in the metal dataset, in particular in the k-means algorithm. Artificial intelligence makes available a very powerful tool that is the principal component analysis. In simple terms, the difficulty that there is for our mind is to represent phenomena that have 5, 10, 15 variables in the space, because our mind can understand better mainly B and 3-dimensional representation in the space. So the principal component analysis is an artificial intelligence techniques that allow to reduce multi-dimensional spaces in bidimensional spaces, retaining all the important information in the new fake variables that are created. In our cases, we were starting from a data set with 91 processes and 5 columns. That means 5 variables that are our impact categories. And through the principal component analysis, we reduced this space from 5 impact categories to 2 variables that we can consider a sort of fake impact categories that represent together all the 5. These 2 fake impact categories namely are called PC1 and PC2 in our representation. But it will be more clear in the next slide what we did. This is the result of the principal component analysis. You can see in blue PC1, this is our first fake impact category. And you can see that high value of PC1 here correspond to high value of particulate matter and human toxicity. Why? Because the principal component analysis found that PC1 increase when particulate matter and human toxicity increase. He could find a direct correlation of proportionality between these variables. At the same time, low value PC1 represent low value of climate change on fossil depletion, as you can see here. For PC2, our second fake impact category variable, high value of PC2 represent high value of water depletion. And in all the other cases, low value of PC2 represent low value of all the others impact category. Artificial intelligence has this powerful tool of dimensionality reduction that allows to retain information from reality and to have a presentation in a bidimensional space that allows, as in our case, to make powerful clusterization, powerful mapping, a powerful comparison about different processes. Because of what we have here. Here we have our metals dataset, okay, that has been classified on this graph, where we have on the x-axis PC1, the principal component 1, that, as we said, for higher value of PC1 means that we have high value of particulate matter and human toxicity. On the y-axis, we have the principal component 2, that we said is proportional to water depletion. So, putting a point for each process on this map allow us to differentiate the different processes, to infer information for our clients that want to invest in a process with respect to
Sorry to interrupt, Madalena.
Yes?
If you could wrap up. Can you hear us now? Because
yes, I finished a few minutes.
I finished.
Yes. As you can see here, we have harmful processes in correspondence of high value PC1, because in this area fall all the processes that have a high value of particulate matter and human toxicity. And we never recommend to our clients, if they have regulatory compliance, to choose materials in the area. As well, to choose materials or processes that fall in this area where you have high consume of water. In this way, we obtained a powerful way to classify algorithm that can also be annotated in this way. You can recognize the process you are dealing, and to show how through artificial intelligence, life cycle analysis can help you to compare and choose better what we want to use and in safer way. Thank you for your attention.
Right. So it's a 45-year-old company. We manufacture construction chemicals and coatings. We are based in Thessaloniki, where the headquarters are. We've got more than 350 products, 7 R&D labs, 3 quality control labs, 8 product categories. Most of them, they are construction chemicals. We also produce paints and surface protection coatings. We have international presence. Apart from Greece, we have 2 more manufacturing sites, one in Romania and one in Serbia. We've got 6 commercial subsidiaries, and we do have clients in all over the world, mainly in Europe, but we also have a strong presence in Latin America, in Asia, and in Australia. So what actually SSbD means for a coating company? So imagine you are building a house, right? And you moved in, and after 10 years, regulators come and they say to you that you have a toxic substance in your house, right? Nobody would ever live in a house like this. So you remember the arsenic and lead-based paints in the past, right? Now they are all banned because they caused significant health effects to both workers and consumers. And so the traditional approach in our R&D sector, in our industry mainly, is cost and performance, right? Think about, you find the most durable binder, and you use it, and you manage the health effects, its hazard later on through PPE or through gloves, masks, etc., etc. So SSbD actually inverts that logic, and now sustainability and safety becomes engineering constraints. So in simple terms, SSbD means, can we substitute this hazardous material without affecting performance? That's what SSbD for us, right? So while I was presenting the idea of SSbD in the company, I got this question, like, why should we implement something which is voluntarily? Apart from the obvious, my reply was, apart from the obvious, that we create safe and more sustainable products. It's about future-proofing your formulation against potential regulatory changes in the near future. But the main one, as it was mentioned in the past, is because the data that will be generated through the implementation and collected through implementation of SSbD will be used in various regulatory instruments, as it was mentioned before. And not only regulatory frameworks and instruments, but also voluntary certification schemes like LEED and BREEAM, right? Where the big construction chemical developers, the construction developers require nowadays. So where we are now as a company, right? We have multiple products with EPDs. We run LCA, like most of the companies in our sector. We do systematic screening of our chemical portfolio against the substances of very high concern, a number of different categories: CMR substances, carcinogenic, mutagenic, and toxic for reproduction, skin and respiratory sensitizers, etc., etc. And you remember before, in my previous slide, I highlighted that the data will be generated through SSbD implementation, will be used in other regulatory instruments. And here is the case. Systematic hazard screening practices required, for instance, by EU taxonomy and CSRD and ESG reporting and the new packaging waste regulation. So for regulatory departments, the implementation of SSbD is a win-win. It's not an additional cost center. So it's like an investment, especially for regulatory departments. And I'm talking about my own perspective, right? So what are the next steps for us? We would like to establish an SSbD team, right? And the main reason for this SSbD team is to train the team, because this is very important. So we want to get together people from various departments, like purchasing department, regulatory affairs department, and the R&D, of course. We want to do the scoping analysis as it is described in our in the SSbD framework, to reply what are the objectives of safety and for safety and sustainability in our products, right? And then, of course, we are not going to change everything in one night. We are going to choose one product to apply, one pilot project, a paint product that we are considering at the moment to implement SSbD idea. So reducing preservatives in paint formulation. This case study actually is close to home for us, right? And I believe it illustrates mostly what SSbD philosophy practice is better than in any other abstract description, like reducing preservatives. As you know, water-based paints, they require preservatives in order to avoid spoilage and product degradation. So, and this spoilage comes from microbes. Most of the microbes, they come from the manufacturing process, either mixing vessel, pipes, raw materials. Disinfecting and water process, right? So disinfecting the water process, cleaning the pipes, going beyond the standard hygiene. So this way we can reduce the amount of preservatives. And why do we need to reduce the amount of preservatives in our paint formulations? The main reason is because preservatives are quite toxic, right? Most of the preservatives in our industry are isothiazolinones. It's a group of substances that they're skin sensitizers. They cause contact dermatitis, even in trace amounts. So using this extreme, going beyond the hygiene standards in the plant and reducing the microbial load, so we can reduce also the preservative concentration in our paint products. So of course, there are many obstacles. Limited expertise is one of the main obstacles. So how can you implement something when you don't really know what it is, right? Most of the companies, they are lacking of expertise with like LCAs. Most of the LCAs are being done by external consultants, so it's hard to coordinate this process. Another obstacle is the high R&D cost. Imagine substituting one substance for another one. You need to test and validate that you have the same performance for your product, which means higher cost. And even any change in the manufacturing process, it leads to higher manufacturing costs. But the main problem, in my perspective, is the data gaps, supplier data gaps. We still use raw materials that we don't have the full composition. We don't know what exactly we are using, and this is pretty standard for all the industry, right? So this is these are the main issues. Maybe for supplier data gaps, blockchain technology will be a good sharing methodology, and as it is described in the new methodology, the SSbD methodology. Thank you for your attention.
Thank you. I will speak about how fossil-based polyester can be transferred to a circular molecule, a circular polyester. This is not just a paperwork. This is not it includes a lot of paperwork, but actually is a product. It's a product available in the market right now. So we are speaking about Pudralac. Pudralac is the brand name of our polyester. First of all, I have to present the company. Megara Resins has 50 years industrial production in three different sites in Greece, in Megara, in Avlida, and in Pyrgos. It has a global resin portfolio, resins for paints, coatings, paper, chemicals, expertise. Most of the building sector all around Greece are among our customers. We are glad to see many of them here in this room. But as far as I see from other colleagues in the platform, we have clients from abroad. So we are glad to welcome you in this meeting. In 3 production units, we are producing powder coating polyesters, gamma rosin derivatives, hot melt adhesives, alkyd resins, acrylic resins, unsaturated polyester resins, polyurethanes, and paper-sized chemicals, as I said before. These are the 3 units in Megara, the first one, the oldest one, in Avlita. Mobile phone, sorry. And the last in Pyrgos. Our company has been certified according to ISO 9001 for quality management system. And also we have implemented several management systems like environmental management system, health and safety, food safety, EcoVadis, and the latest one, ICC Plus, which is approximately the scheme that we have been certified for the circular polyester. All these certifications are combined with our vision for net zero. We are obliged and have committed to meet zero emissions targets up to 2040. We are achieving this goal. We are by transforming not only our energy, our prime energy sources, but also by transforming our raw materials. Our example is to solve the linear problem of chemical industry. You know, chemical industry is a fossil-based feedstocks, mainly crude oil, natural gas. We have finite resources and high carbon intensity. This is the problem all around chemical industry. This is the linear production model where we extract the raw material we produce, we use and dispose. This is the typical linear model we can meet all around industry, especially in chemical industry. Of course, we have a little material of recovery in general case, not focusing on special cases, but in general, and abundant carbon is lost. So we have systemic consequences, high GHG emissions, resource depletion, regulatory pressures are, as already explained. Concerning the resins problem, resins mostly rely on fossil-based raw material, coatings markets, as many companies are among us, requires circular, biocircular, bio-based, carbon bio-based products. So what is Pudralac? Pudralac is a high-performance polyester resin. It's the core resin behind powder coatings. It's the resin that we use to paint metal surfaces, mostly from aluminum. So what it does, it binds the coating system. It defines performance of the coating and determines the durability of the product. It is used mostly in metal surfaces, in architecture and industrial applications. Why it matters? Because powder coatings are already low impact. No, it's a low impact product without hazard properties, without toxicity. But the resin is still a fossil-based resin because most of the raw materials comes from the distillation of crude oil. In Megara resins, we are doing somehow the opposite cycle. We are a polymerization unit. In Megara resins, as I said, we are doing polymerization. We are producing polymers. And you may be familiar with depolymerization, exactly the opposite steps at the opposite position where the polymer can turn back to its monomers. This is the basic idea what we have done. We are using monomers that have been derived from depolymerization processes. So we're speaking about the same molecules with different carbons, different carbon feedstock. The fossil feedstock, it's already known from crude oil. We have the refining in petrochemical industry to produce olefins, and olefins become useful raw materials for our plants as neobedyl glycol, NPG, which is actually one of the main raw materials to produce the polyester. The second road that we have implemented, that we have used to produce the new product, is from waste. Waste turned into olefins by pyrolysis process, a total unique process where the polymers are cut into its main building blocks, like monomers, and we take the same molecule, as I said before, NPG, neobedyl glycol. This circular strategy is based on the mass balance. I will explain more in details in my next slide. So mass balance is a strategy that we use to produce this new product. It depends on 25 up to 50% of circular NPG that we are using in the same reactors than the conventional grade of Pudralac. And of course, it's very scalable because we can increase and produce in all our reactors without changing the temperature, the pressure, or other conditions. As I said, behind mass balance approach is that we can combine recycled feedstocks like circular and biocircular NPG with fossil feedstock, fossil NPG, or other raw materials. NPG is just an example. It's just the first step that we have made to make Pudralac greener. But we can do it in all our raw materials as far as they are available in the market in a logical price. So we are combining these same molecules but different carbon feedstocks, which are physically mixed in the tank, physical mixed in the process, physical mixed in the reactors, and we are making the polymerization, the production of polyester. So the final product has a percentage of fossil feedstock for sure, a percentage of recycled feedstock as well, and we have some pure total green polyesters. This is a mass balance approach that we are using right now. Of course, segregation is something that we can be made in our plants, but for the moment, the market asks for mass balance products. Again, for the impact, we have a sustainable sourcing based partially or fully on renewable and recycled raw materials. We are reducing CO2 emissions by providing PCF, lower PCF products with lower PCF that can be used to decrease your scope 3 emissions, the emissions that are combined with the raw materials and subsequently with your products. To differentiate orderings, adding value to you and your supply chain, to all sectors that are using polyesters, and immediate shift. We use drop-in solutions without need for excess R&D and take a lot of time to use in R&D processes new raw materials and new products. It's a drop-in solution. And of course, it is based on a traceable mass balance concept that has been certified according to ICC, as I said before. As a final impact, we produce a polyester that has 20% lower GHG emissions. It is available now in the market, and it is a circular carbon. If you not know ICC, ICC is a voluntary scheme, comes from Germany, but it's well known all around the world. It has approximately 30,000 certificates right now out there. Most of them are in fuels industry, but several chemical industries, more than 200, have already certified according to ICC. Mega Resins is from 2025, certified under ICC for 2 of its plants in Megara and in Avlida also. This is our certificate. You can see there that our input material for now, it's neopetyl glycol, and we are producing, as I said, the polyester named Pudralac, which is actually the same product as the conventional Pudralac in compared to properties. Our future for circular economy is to have 100% sustainable polyesters from circular and biocircular raw materials. And to close my presentation, please remember that small actions create big impacts. Thank you.
Good morning. Thank you so much for the invitation. And I'm Emanuele from Tecnochimica in Italy. Our company is in the field of galvanic. We produce a product for galvanic. Tecnochimica started more than 40 years ago in Milan, Italy, and our focus is always to be present to our customer like a supporter, like a partner. The continuous growth of Tecnochimica can give to us the possibility to work not only for the future but for the present, because we trust that the secrets are new technology for the future, but the evolution of the old technology for the present. Now we have all the certificate like the ISO for to be allowed to work with the big company, big customer, and big end user in Italy. And these are a lot of our company that we work. So in USA, we work with Columbia Chemical. In North Africa, Metapro, as you can see, AFM and Politecnico in Milano. And for the precious metal with Consortium Physics. All our technology and are certificated by ISO and NIF also for the cybersecurity problem. And we are always in work to develop, as I say before, for change the solid technology. One example is a study that we make with our friend of Mozart, where we can eliminate the acid boric acid inside the electrolytic nickel bath with a normal composition to avoid the present, as I say, of boric acid inside. We study a special buffer solution that can work with no change of pH inside the bath and can work together with another composite for the realize of the hardest layer in the end. Thank you so much.
Good morning. Thank you very much for the opportunity to present Himare Labs. Himare Labs is an SME company located in Thessaloniki. We develop technology for the wood-based panels industry. We are active worldwide. We are in the field about 50 years. Next year we will close quite 50 years. We are a team of about 30 people. Most of us work in the technical support department, where we visit on site the industry and apply our technology. And we also have the R&D department where we develop technology and participate in projects funded by the European Union or by the company itself or by our clients that ask to develop specific things for them. Today, I will speak about an overview of the field that our company is active in, the basic concept of the SSbD, although you have already covered this topic, specific information about the SSbD in the wood-based panels sector, how is the situation today, the challenges and the best practices, and an example of the contribution of our company in the SSbD through a European project. Well, what is actually wood-based panels? Wood-based panels is a product that we have in our everyday life. It is particle board, MDF, plywood, OSB. We see them in furniture, in construction, in packaging. Of course, you have used it in your houses. It is a sector that produces hundreds of millions of cubic meters annually, and it is quite natural material, I would say, as the binder, that it is the resin. It is about 10% of the total product, while the rest is wood. And you can find it in various forms and various kinds regarding the properties, so it's to be suitable for the various applications. In 2024, the market size was about 200 billion United States dollars, and in 2030 it is expected to raise to 284 billion United States dollars. This growth is driven mostly by the construction, furniture, and automotive demand. You have already referred to SSbD concepts. In a few words, it is to make safe products, safe for the environment, the people, and the society, and sustainable to last through time, and of course, all of them to take into consideration the economy of the whole chain values. The strength of this concept is that we have to follow some standards, all of us, so as to know that we speak the same language. Of course, this has a weakness because it necessitates some complex documentation and some regulations that we have to comply with. And sometimes maybe some companies cannot comply with this, so it has a risk. But it is an opportunity for the industry to make better products and go to more to give some quality in our life. Regarding specifically for the panels, the risks that we face are to the chemical point of view and to the side of the manufacturing of the products. Regarding the manufacturing, we have the dust. When we make wood-based panels, we have a lot of dust that perhaps they can lead to explosions, so we have to take measures. There is the noise and the machinery that, of course, has some risks. And there are the chippers, the dryers, the presses that also put some risks to the people that were there. Regarding the chemical part of the wood-based panels, as I told you, we have the wood that it is, of course, a natural product, but we have the binder that it is about 10% of the whole product, and until now it is a fossil product. And most of the resins used there are formaldehyde-based, that, as we know, there are some studies that pose some risks for this material. And last, it is the recycling, because at the end of life, this material has to recycle safely so as not to leave wastes to the environment. And of course, manage it in a way that will prolong its life and contribute to the sustainability concept. Now, what has to do? It is to make a safe operation and design, to eliminate the risks by automation, to redesign the whole material, as it was said before. Safe and sustainable is about about innovation, is about creating new processes and new products so as to eliminate all the risks to the production lines. Use less harmful binders, if possible to have only bio-based raw materials for the binders, and also redesign the recycling of these products as to make zero waste products that do not burden the environment. What is the situation today? Today, in the field of wood-based panels, there is actually no safe and sustainable implementation. However, there are sporadic actions by the various industries that implement some part of the concept that included in the safe and sustainable principles. As it is voluntary, as you understand, the industry has no obligation to adapt the regulations by the European Union. And the whole attempts, the whole efforts are based on the voluntary basis of the industry through EU-funded projects mostly. So we have to make the resins, we have to develop the resins, the coatings, and the recycling systems in order to improve the safe and sustainable concept in this field. Pioneering companies in this is Egger in Austria, Kronospan and Swiss Kronos, that they have moved to use low emission or formaldehyde-free resins, bioadhesives based on tannin, lignin, or soy, to have a closed-loop recycling system of wood, apply environmental product declarations, and take care of the energy in order to have a sufficient system using the biomass residues. However, as I told you before, all of them are not characterized as SSbD implementation system, but as sustainability strategies or eco-design or circular economy parts of the whole safe and sustainable system. Why it has not been implemented yet? First of all, because so far it was volunteer. It needed to spend money for this. There is a delay to the managers in order to change things. So here we need a strategic leadership and a management commitment, as well as a clear communication for the benefits of applying SSbD. Of course, if you proceed to this way, there are some threats like spending a lot of money or have delays to a successful outcome. But it will be for the good of the product themselves, the society, and the economy general. We need training to all levels of the hierarchy of industry. We need transparent communication, and of course, we need active engagement of all people working at the various levels at the production of these products. How HIMAR contributes to this. HIMAR participates in SSbD European project, where the full title is Sustainable, Safe and High-Performance Bio-Based Adhesives for Wood-Based Composite Materials. It is a project that started in October 2025. It will last 48 months. In this project participate 2 large companies, 5 SMEs, and 8 R&D institutions. The total budget is about 9 million euros, and the contribution of the European Union is about 7.5 million euros. So what we do here, first of all, we develop resins that are bio-based, that are totally bio-based. Specifically, Himar develop resins that are from organic acids and proteins, or organic acid and sugars. It is one pathway, and the other pathway is polyphenolic materials like tannin, that it is combined with furfural, and to this we add some also natural raw materials like protein and lignin and other to improve the performance. These resins are applied in 4 types of wood-based panels: particle board, MDF, plywood panels, and insulation panels also from wood insulation panels. They are produced at lab scale, pilot scale, and demo scale, and also these products are going to be recycled following 3 different methods. In order to testify the effectiveness of the recycling, both the wood and the resin that will be recycled will be used again to make new products. The whole project will be under a safe and sustainable by design study carried out by an institution that will guide us in order to follow the rules of the safe and sustainable. So here in this project, safe and sustainable by design is something that follows us from the beginning of the project, and not something that it is calculated at the end and we say that we will do it in another project. We have to follow it in this project. So this is all. Thank you very much.
I'm an assistant professor in University of West Africa, and was also very glad to be also calling in recently in 2025 with this great team, Alexandros, who had the initiative to arrange this great workshop. And of course, I would like to thank you for inviting me to organize this panel. And this panel today is going to address some key challenges related to the implementation of SSbD solutions in reality. So, and to do so, here we have 8 people in the field from milestone EU funded projects. Today, let's say, structure, we're going to listen to their presentations, and in the end, we are going to spend some time for a couple of questions that I'm going to pose to them. So, let me briefly introduce them. We have Dr. Stelios Vikos, in Greece platform, and also considered a representative of the EU's project. Then we have Dr. Mirel Bowman from Material Nova and coordinator of Biosourcing. We have Professor Luca Paganin from Politecnico di Milano and coordinator of the Monster project. We have Johannes Seif from Indener and coordinator of ProPlanet. We have Dr. Ayana Nikolenko, senior researcher from NEOTEX and also coordinator of the NEOTEX project. We have Karen Martins, researcher at ISQ and also coordinator, co-site representative member of the Safari project. We have Mirko Valencenzi from Gaza Grupo and also Gaza's coordinator of the Premium project. And finally, in this panel, we have Dr. Raquel Rodriguez from Tecnalia and also coordinator of the Tornado project. So thank you very much for being here. It's a very great pleasure and honor for me to be with you here and having the chance to join this panel. And okay, so the time is very strict already, so I have not lose any more time for the introduction, and I would like to call to the panel, to the podium, the first speaker, Dr. Stelios Vikos. So while he will prepare himself, I will just say a few words. So Dr. Stelios Vikos is a chemical engineer, multiple subjects like sustainable chemistry, energy transition, and industrial innovation. And he's also a representative member from the Irish project. Milestone for the visual support action project. And he also serves as the coordinator of the SSbD CR, which is actually the Greek technology platform for sustainable chemistry. So whenever you're ready,
getting there. All right, well, hello everybody, thank you for being here today. We've heard a lot about SSbD, and this is a session where some of the active projects will be presented. So I'm very happy to present IRIS, perhaps one of the first ones, and one that tried to bring together the needs for research on SSbD so that it can be adopted by industry. So it has been a project highly industry-led, and trying now to see how this works. Doing very well. All right, okay, sorry, it's my file. Let's see how this works. Then page down. Nope. All right, we found the buttons. So IRIS became a project through the Sustainable Chemistry Technology Platform run by CEFIC at the time in 2022 in order to create a common understanding among practitioners and researchers, building an SSbD community, which was the final target, create some knowledge transfer among value chains, create a science, policy, and industry interface, which was seen as being critical for SSbD to succeed. It created roadmaps for research agendas and trying to accelerate industrial uptake. And this was perhaps the carrot, if you like, because by creating roadmaps for research agendas, one could feed into the Horizon work programs and therefore create the financial incentive for people to deal with SSbD. And of course, to contribute to the improvement of the framework and therefore help the Commission go into something that will be operating, it will be easy to operate within companies. So IRIS brought together various groupings. First and foremost was industry. It dealt with there's 7 here, more than 7 here, there's 8 industrial sectors together, those that were deemed in 2021-22 as value chains of priority in the EU. Starting, of course, with chemicals in general, with CEFIC in front. Then construction chemicals with EFCC, automotive industry components with CLEPA. Fragrances came late on, IFRA. IPC dealt with packaging mostly. The Fibers, Textiles and Clothing European Technology Platform for Textiles. INL, the Iberian International Nanotechnology Laboratory, came in for the electronics materials. And CEAR is a new joint. It actually was preceded by EMIRI being the Energy Materials Initiative by Solvay at the time. But EMIRI has now gone into IMI, which I'll talk in a bit about. And therefore, CEAR is the sectoral representative of energy materials. So all of these value chains came together to tell us what they see in SSbD, where they lack, and how they could make progress. On the research and innovation side of things, IRIS linked up to PARC, the Partnership for the Assessment of Risk of Chemicals. Obviously, Horizon Europe, which was the target vehicle for advancing SSbD, and Integrano, which was the nanomaterials equivalent kind of initiative, and with which very close ties exist to date. For policy and regulation, names that you know all about: European Commission, the ISO organization, CN, and OECD. OECD has its own SSbD initiative, its own sustainability and safety initiative, within which IRIS also fits. And in terms of other initiatives and organizations within the EU, mostly, you can see NSC. NSC has been mentioned by Eva Balsamy-Jones earlier in the morning. SScM, which now exists as a sequence of national technology platforms for sustainable chemistry. Change Chemistry, which is the only US proponent in this total. ISC3, a German initiative for sustainable chemistry. IMI, very potent advanced materials initiative, industrial initiative within the Mats for EU partnership. SSbD Innovation Hub is the Dutch initiative, and EU MAT, which is again an umbrella technology platform for materials. So IRIS sits in the middle of all of these, and its ambition is to be exactly that, the umbrella that link policy, industry, and research in this quest of bringing SSbD into everyday practice in industry. So key outcomes from the value chains, that's what we're created to do. I won't go into the words because the time is not permitting, but basically we wanted to check each value chain and get results from them to say where will they stand and where they want to go and how they need to go there. So which are the gaps to address? And these were lack of harmonized and easy to apply tools and protocols. So tools and protocols is a major issue. Open database was mentioned in the morning as well. Very, very critical, perhaps the most critical of all. Uncertainty of the safety impacts at the early age of development. This is, again, a dimension that is often forgotten. Many people do exactly what the SSbD framework requires us to do, but they do it late on. They do it when the material or the chemical has already been developed with a lot of expense. So early stage assessment is the critical bit here. Another problem for going forward is the internal experts, lack of, we know that, and problematic assessment for complex products, which still persists today. And a full assessment at late stages of innovation is what I've just described. In other words, a lot of effort about detailed assessment is done late on when a lot of money and effort has been spent, and going backwards is not a business preferred solution. So IRIS came up with a supportive industrial roadmap for applying SSbD, so to create the bridge between the status quo at the time and the target status. And this was published in 2024. I mean, obviously you can't read the text, and I can't read it either, but we'll concentrate perhaps on two sides. The research needs. The first research need is how to implement SSbD in the innovation process. And you saw now the revised framework that Professor Balsamy-Jones presented in the morning is essentially a spiral going from the very early uncertain stages down to the market end, where everything is almost known. Further development of LCA methods, and you've heard about AI implementation on LCA now. It's the sort of vogue of the day, to go and enhance LCA methods to incorporate not only environmental sustainability but all the rest of the vectors of SSbD, and to make that easily applicable and repeatable. Updated and new data sets and databases, that goes into the FAIR creation, the FAIR data creation we've all spoken about and we know about. Complementary methods for risk assessment and sustainability assessment. And that is essentially bringing together the notion of risk to human health and sustainability, meaning risk to the environment. So if you think about it in this way, then it's one framework with different vectors. Traceability throughout the value chain is breaking down the silos and talking to the whole value chain from the extraction of raw materials down to the users, where traceability comes about. And it's not easy, It's contrary to a lot of human resistances, but it's there to be broken and traceability to be brought. Implementation of circularity along the value chains. Well, sustainability does include circularity. It's just that circularity has not been that prominent in people's minds for a long time, and that's why it's brought out as a separate kind of dimension. Now, the bio-based alternatives, which is the new sort of the next research need, is where there is quite a lot of work already done, but it needs to be brought to such quantities and such regularity that it's not considered as an oddball, as just a minor kind of oddity. Alternatives to the critical raw materials, that comes from the strategic autonomy kind of need for Europe primarily. But it also boils down to impact to the environment, because once you create alternatives to critical raw materials, essentially you don't need to mine as much, and you don't need to disrupt, therefore, the natural landscape and the lives of local communities where this is done. Efficient recycling methods, well, we've got at least 20 years of action on that one, so it just comes down to finding the right chemical and biochemical process to do it and do it efficiently. And finally, development of services and non-material alternatives. This is, I think it points to the thought of selling chemicals, for example, as a service rather than as materials. And that, again, is a novel thought that needs a lot of cultivation to flourish. Okay, going from research needs, which would feed into things like Horizon and create programs, calls, and funded research, you go into skills and knowledge, and that's a softer aspect, which is critical. We mentioned that at the beginning. Strong skills and safety. We heard this morning arguments as to what safety means and how far we are prepared to compromise human life and property to the aim of producing chemicals. Innovation, technical skills, skills on sustainability, which are less mature. We hear it's not that they're less mature, they're less clear, and they're far more multidimensional. We need, it says here, SSbD requires a general understanding of chemistry and material science and system thinking. And I will stress system thinking because that's where SSbD comes, really. I don't believe anybody created processes and products without them being safe and sustainable to a degree. The point is, how much sustainable do we want them to be? How much safe do we actually tolerate them to be? And how we link all of this together into a coherent total so that we see it from a higher above kind of viewpoint, and we don't bury ourselves into the particularities of the particular material, particular process, particular enterprise. So system thinking is highly important, and it's perhaps enabling tool to make SSbD come closer to a practical tool. And along the value chain we spoke about, and call for a common tool, as it says here, adjusted to the sector. Which sector? Well, we spoke about the 7 value chains. There's far more. Wood was one that we didn't touch in IRIS, but it's also applicable to that. So there's an IRIS industrial roadmap which is coming on, and into that we want all the national technology platforms of the SSchem European Technology Platform to contribute. There's 14 to 16 of them. So we hope that within this year and probably beginning of next year, we're going to have a far more distributed kind of outcome. Perhaps I will skip this and go directly to the IRIS International SSbD community. The IRIS project was not created just as a project to get money. It was created to create It was brought about to create an international SSbD community. It had as a vision to bring all the practitioners from industry, research, and policy together into one total, where they would be able to exchange information, promote their knowledge, create and develop more tools, create opportunities, funded opportunities to do all this, create a sense of commonality, a sense of common ownership, and also in the end be able to provide expert support to those that don't have it because their company is small, because the beginning of their R&D is right now, and they don't have enough depth and so on. So essentially, create a focal point for SSbD. In the IRIS International SSbD community, we have also the NSC community we spoke about, and vice versa, of course, and we collaborate very closely with PARC, with their toolkit and their initiatives. So just one plug, last plug, SSbD 26 in Stockholm in Sweden, 9th to 11th November, nice cool weather. Do come and learn more about SSbD by the experts worldwide. Thank you very much.
Because really very nice, very promising to integrate different languages, ecosystem way of thinking. One way is thank you. Now we can go on with the next, let's say, 5-minute presentations. As it was mentioned in the program, I've already kindly asked our presenters to be fast as possible. So next we have Dr. Mireille Boltman. While the presentation, second point. Okay. A few words about Dr. Mireille. She's from Material Nova and coordinator of the Biosocial project. She holds a PhD in sciences from the Université Libre de Brussels, and next joined Material Nova as a researcher in chemistry and robotic coatings. And since 2014, she served as an R&D program manager, supporting the organization strategy in safe and sustainable circular materials. While over the years, she has contributed to numerous regional and international R&D initiatives, coordinating several programs. So the floor is yours. Thank you.
Thank you. I'll make it short, promise. You can come on Wednesday for the full presentation. So we are now talking about the BioSushi project, which has as objective to develop 3 SSbD PFAS-free bio-based coatings for water and oil repellency. And these coatings validated in 3 case studies, which are textile coating, food packaging, in fact, a paper food tray, and glass cosmetic packaging. BioSushi methodology is really based on 3 pillars. You have the coating developments or R&D coating activities, and the safe and sustainable by design, and computational modeling. Okay. There are 3 types of coatings: bio-based powder, this is mainly for the food tray, and 2 family of hybrid sol gel coatings. One more water-based with high organic content, and one partially solvent-based for the glass packaging case study. In all of these, we are exploring additives that will be able to provide the same performances than the PFAS-based, but of course with safer and more sustainable targets. So a bit more information of the safe and sustainable by design application in this project. So we started with the scoping analysis. We are in a design and redesign aspect depending on the case study. So scoping analysis, including specification, and then starting with the preliminary identification of components. Then we really went into the coating development aspects with formulation trials, performance evaluation, and some physicochemical properties. Computational tools were used to assess the preliminary safety aspects, and then were complemented so by data mining coming from all the safety data sheets and information that are available. Then we also used QSAR and predictive models. The computational model tools also includes physical modeling, and all of these are entering a data lake to make all this data available for the future. Risk assessments was based on the data, the modeling, and also some experiments. So it's nice to see that we could also assess some hazard properties by screening electrochemical tools. And the project includes, of course, the sustainability assessment by life cycle assessment, life cycle costing, social life cycle assessment, and also social acceptance and willingness to pay. These are the main actors covering all these aspects. We are 15 partners with several partners covering the SSbD aspect. We have a partner specifically covering social acceptance. The 3 case studies were covered by 5 partners, and we have the industrial validation included in the project. And I will stop now. I think I'm okay in terms of timing. Is it?
Great.
Thank you very much. Now we could also go on with the next short presentation from Professor Luca Mugani, the coordinator of the MOSER project and full professor in applied physical chemistry at Politecnico di Milano, with expertise in surface engineering, electrochemistry, and functional coatings. And his research focuses on electrical deposition, advanced surface treatments, sustainable materials for applications in microelectronics and storage, and also for industrial coatings. Thank you, Professor.
Thank you, Kostas, for the introduction. Good morning, everyone. A few words about the MOSER project, that we are almost at the end of this project. So by the end of May, we should be able to conclude everything. We have a lot of partners, as of course, usually in this project. I just want to mention where is somewhere. University of Birmingham. So we were on, let's say, on the safe side of this SSbD because Eva was working with us, and so no problem from that point of view. What is about MOSER project? Actually, is the idea is to trying to find a solution or at least an alternative to hard chromium plating. So basically one of the most common coatings in order to reduce wear and even also to improve corrosion protection. And the idea was to propose composite plating. So the main sector is plating, and if you know what is plating, part is an old technology with very consolidated formulation, as also Emanuele from Technochimica mentioned in the previous lot. But is actually the very nice example for us to in order to apply the SSbD strategy, because we need new formulations, safer formulations. We need also decision tools. So many of the let's say names and words mentioned in the previous presentation can be exactly applied here in this field, and we try to do this in this project. Composite, you see here a cross section, means that instead of having a bulk layer, you have a matrix. In this case, metallic matrix with nanoparticles embedded. What about the, let's say, of course, we developed the technology to apply these composites. We have done also, we applied these layers on demonstrators. We proved that the new coatings can be an alternative, at least in some specific applications to hard chromium, but specifically related to the SSbD strategy. What we have done is that, let's say, that there were two major, let's say, contribution to this. One was in the formulation of the bath. Okay, so especially based on artificial intelligence or machine learning, call as you want, we designed since the beginning a new electrolyte, avoiding some chemicals, which are a matter of concern for some regulations and all the new regulations in at least in Europe. And the other one, for this aspect, is a major step in the plating industry, because consider that many of the formulations used today are old, like 50 years ago, probably 50 years old. The other one was the decision tool. So again, also this was missing in the sector. So the idea to decide which is the best coating, not only in terms of functional properties, but also in terms of sustainability.
And so we implemented this, and so now there is a tool that operators can use, end user, for instance, can use to design the coating since the beginning, okay, of the project, of the design of the component, which is absolutely missing in this sector. Here there were packages, nothing new, and just to save time, yeah, we have the end was planned last year, but we had a 6 months extension, so we will close the project in November. Just few other things. We deal was mentioned also the idea of the regulation at the European level that should match with the new strategy, and that is the example. Some of the elements here are a matter of the REACH regulation, which is the registration and the use of the chemicals, and so we need to find a way also to be compliant with this regulation, otherwise all the metals will be excluded. And then especially want to stress again the decision supporting tool, considering the kind of chemicals, the safety of the chemicals, the use and the properties that of the coating that you want to achieve. I think that with this should be okay. Thank you.
Completion of most of the project, and now I'd like to call Johannes Seif from there, and also coordinator of the Planet project. He's a physicist with a PhD in material sciences and a strong focus on computational modeling and advanced materials development in the company. He's the coordinator, as said, in Planet project, and he's committed to driving innovation that supports a more sustainable and energy efficient future. So whenever the presentation is ready.
Thank you, Kostas, for the kind introduction. It's a great pleasure to be here today and talk to you about ProPlanet, and also a great pleasure to represent the ProPlanet team, which I have here on the next slide. So we are a team of 13 partners, as you can see, spread all over Europe, from the north to the south. And our project now also is finishing actually this month. And during ProPlanet, as we already heard also from our sister project from BioSushi, it's along the same lines, obviously. So what we did in ProPlanet was to find alternatives to PFAS-based coatings, namely for three different sectors: the textile industry or textile coatings, food packaging coatings, and also glass coatings. And this has been done applying different hybrid coatings for these different use cases. But at the same time, we also developed a decision support tool, or a tool that helps us to understand more in detail how the material performance can be affected by different choices of materials or substances, but also how these substances impact the environment. So where do they end up in which kind of compartments in soil, in water, in the air, and so on. And besides that, we also had partners working on, obviously, on SSbD and this whole aspect of designing the coatings before implementing them. So that covered also life cycle assessment and so on, as well as social life cycle assessment. And some partners were working also on the roadmap towards standardization and certification. And in total, we were all working, of course, using the expertise of all the partners towards a way to implement new coatings and apply them to the different use cases by really having something viable and ecologically friendly. And with that, I want to thank you all for your attention.
And now we'll go on with the next project from Dr. Ayana Nikolenko, also coordinator of the NEOTEX project, and supports a senior researcher and project leader in coatings in sulfur treatment unit at the SSbD, sulfur engineering in Spain, specializing in electrodeposition and scaling up of electrodeposition processes to pilot production lines. Supposed PhD in physical chemistry, which was awarded by the Vilnius University in 2018 for the development of environmentally friendly metal plating baths. So, what I'm reading, floor is yours.
Thank you. Thank you for the kind introduction, Kostas. Hello, everyone. So the time is tight, so I'll be direct. NEOTEX. NEOTEX is one of the 4 projects that was funded under Horizon Resilience call, topic safe and sustainable by design metallic coatings. So it is one of the 4 projects in the 4C cluster, together with Mozart, Free.me, and Nouveau. The main motivation behind the NEOTEX is the need to find platinum substitutes in materials for energy and digital storage applications. So these sectors heavily rely on the use of platinum and other platinum group metals, but we know that they are very scarce, costly, and also have a very high supply risk. So in the project, we focus on the 3 use cases: the development of metallic coatings for water electrolysis, for PEM fuel cells, and also for the digital storage devices. And in each of these use cases, the SSbD approaches are integrated. So in the project, we have a partner who leads the development of the SSbD methodologies. This is Iris. So this is done across 3 different use cases and at 3 different levels. So we start from the laboratory scale developments, then the scale up, and then also the creation and validation of the demonstrators. So here different elements are combined. For example, LCA and LCC, chemical risk assessment, recycling, and also the materials modeling part. So all this data is then fed into a decision support tool that aims to integrate the results from different assessments and also the information coming from different partners. And here I had a part on the perspective, which I'll probably skip because of the time, but just to say that the perspective is very bright, and maybe move on to the key challenges that we identified in the project during the implementation of the SSbD approaches. Most of them actually were already mentioned during today's presentations, and one of them is the generalization gap that I wanted to highlight here, because it is absolutely not the same to apply methodologies, the SSbD methodologies, for example, for electrodeposited coatings or for the physically deposited coatings. So the SSbD solutions here need to be tailored, need to be case specific. So in the project, we have identified and have proposed some suitable tools that are specific for the coating sectors. But here another methodological challenges that we faced is that the application of the SSbD requires early stage decisions, but the reliable data come only late in the development. So early decisions are taken under uncertainty. And here's where actually we see that the materials modeling can help. And we have seen today a few very nice presentations on that, but also, for example, in silico assessments can provide the data for the early stage assessments. The data issue is even more complex actually than that, because we all know that it's very difficult to get good data on the brand new technologies, but especially under industrial confidentiality conditions. And even if we have this data available, there is also a lack of standardized data sets. So from the NEOTEX, for example, we pushed the use of shared data infrastructure. We also enable some mechanisms for the confidential data sharing, and we also contribute to the standardization by proposing some methodologies for the data collections, but they are very use case specific. And finally, So we know that SSbD requires combined expertise in many different fields, also requires different experts to talk to each other, but we don't always speak the same language. For example, I'm coming from the experimental material science background. I don't do SSbD assessments myself, but I want to implement this framework in the experimental day by day. So a solution here is the creation of modular decision support tools, like one that we try to develop in the NEOTEX effect, where each model is created by experts for non-experts, so that using the sustainable decisions does not require being an expert in all 5 or even more different fields. But that's, of course, a separate topic for discussions, and I think that for now, that is it from my side. Thank you.
And now we'll go on. Dr. Carla Martins, she's a researcher at ISQ and also as a representative member of Safari Project. So she holds a PhD in chemical engineering from Nova University of Lisbon and has a background in gas purification and CO2 removal, while since 2021 has been working in occupational exposure assessment and risk management, focusing on advanced materials and technologies.
Thank you.
So, whenever presentation ready.
Okay. Thank you for your kind introduction. Good afternoon or good morning. So I'm here just to talk very briefly about Safari project. This project follows the development of 2D materials, specifically graphene MX hybrids, based on SSbD principles. So the project is coordinated by Poznan Institute of Technology, and it started at the end of 2023 and will be concluded by mid-2027. The main aims of the project is, as I said, develop 2D materials for advanced applications by accelerating their commercialization and revolutionize performance by improvement in materials quality and controllability, together with the development of safe and sustainable production processes. The formulation developed will be then validated and demonstrated in 3 test cases, which are the sensors for glucose and lactate, conductive inks, and electromagnetic shielding coatings. So these materials are actually highly promising. MXenes, they derived from carbides and nitrides, hexagonal structures. And because of this, they offer exceptional properties such as high electrical conductivity, high mechanical performance, and chemical stability. However, their production processes often relies on the use of hazardous chemicals, which raises, of course, environmental and health concerns. This is where Safari project comes in. So Safari methodology, of course, follows the implementation of SSbD framework in the early development stages of these 2D materials, not only to attain highly performing materials, but also safe and sustainable throughout their life cycle. We are implementing these SSbD 5 steps in parallel, and all the information is being integrated to support informed design and redesign decisions. So about the intrinsic hazards, this project is being based on IATA Decision 3, where all the chemical substances that they are being used for the production of these new materials are being assessed and scored and ranked in order to recommend safety measures in line with SSbD principles. So those substances that were not found in literature and in databases, they were selected to be tested for toxicity profile within this project, together with the new materials. So we are creating ecotoxicological and human toxicological profiling, together with in silico predictive studies, which have been suggesting that these new materials have actually low toxicity. On the other hand, implementing the evaluation or establishing safety protocols about based on the assessment of workers' exposure, potential workers' exposure to nanomaterials and nanoproducts, in order to define risk prioritization and provide informed recommendations for safe by design strategies. We also being implemented, of course, LCAs and LCCs in order to determine which will be the actual impacts and to have as much as possible these sustainable materials. But actually, at the moment, the highest major achievement of this project, of course, is based on what I said about these steps, is actually the alternative process that overcomes the use of toxic hydrofluoric acid etching by relying the process on a more physics than a less chemical processes, by using lower power microwaves for etching and high performancing acoustic waves for delamination. So to conclude, I want to give you some key points, is that, of course, you know that SSbD is critical and is in line with EU policies and EU Green Deal. On the other hand, we've been found that environmental safety, performance data is somehow challenging to be integrated, but this is very critical to inform decisions. And finally, I didn't mention in the beginning, but actually this project is an active partner in the graphene flagship, which is very tightly connected with industry. And in particularly, we are bringing SSbD within the European graphene framework, roadmap, sorry. And for me, that's it. Thank you for your attention.
Now to go to the next project from Mirko Bossenzi, who holds a degree in materials engineering from Politecnico di Milano, and for the past 2 years have been working as a head of the R&D as a group of coordinates the PRIMI project. He has a transversal corporate role across the various laboratories of the group, and he's mainly involved as a process engineer with a focus on the aluminium mineralizing and electrolysis nickel plating. Thank you, Mirko, for being here, and floor is yours.
Thank you, Kostas, for the introduction. Good morning, everyone. Before starting to talk about the FREEME project, I want to do a brief introduction of my companies. Gruppo Gaser is a group of companies based in Italy. We have 12 companies, 11 in Italy and 1 in India. All companies are specialized in surface treatment, in particular aluminum anodizing, nickel electrolysis, and functional polymeric coating and heat treatment. Gruppo Gaser is a coordinator of FREEME project. FREEME project is a Horizon European project starting in 2022 with a duration of 48 months. So this year is the last year, and I arrive in conclude this project. The FREEME project as a principal goal, they created a sustainable metallization on plastic process. In this slide, we can see the actual process of plating on plastic with a presence of chromium hexavalent etching, a neutralization and activation with collodium palladium, and a reduction, and the final electrolysis nickel with electroplating. In this process, we have 2 big problems: the presence of etching with hexavalent chromium, that it is a very dangerous substance with limitation by Richard Rose, and the presence of palladium colloidal. It is considered rare material with poor supplies and very high cost. So with FREEME, we have proposed 2 solutions. The first solutions proposed by Polytechnic of Milan is a sprayable solution with a synthesis of composite resin with a metal precursor, and spraying this resin on the plastic, we obtain thin film of resin that can be activation with a nickel reduction, and then we can perform electroless nickel and final electroplating. The second solution is an immersion solution developed by C-Nano companies with a chromium mesavalent free etching process and palladium free activation process. With FreeMe project, we have a perfect example of application of sustainability and safe by design strategy, because we have a safe by material designing with a replacing of chromium, and sustainability by design with a replacement of palladium. With FreeMe, we touch economic, environment, and social sustainability, and with a multi-criteria decision analysis, we have a perfect SSbD approach. Thank you.
And now we're going to move to the last presentation from Dr. Raquel Rodriguez. She works as a project manager at NALIA Research Center in Spain and the Sustainable and Functional Polymers Department. She has extensive experience in the synthesis of functional and bio-based polymers, such as polymeric binders for coatings and adhesive formulations, chemical recycling of polymers, and micro capsules containing active substances, including gases in self-healing, PCM slurries, and fragrances. Her PhD thesis focused on silicon modified acrylic nanoparticles by minimals of polymerization. And of course, the floor is yours.
Okay, thank you very much for the kind introduction. I'm going to present Tornado project. Tornado, the title of the project is New Routes of Safe and Sustainable by Design Water and Oil Repellent Bio-based Coatings. And the main objective of this project is to develop new bio-based coatings, organic and hybrid ones, and validate them in 3 different use cases: packaging, food contact packaging, textiles, and cookware. So all of them are validated in consumer products, and the coatings will be developed following the safe and sustainable design principles. Okay, so as I said, we focus on the development of new bio-based coatings in 2 different lines. The first one was the waterborne PFAS-free bio-based acrylic coatings with water and oil repellency. These coatings were designed from the beginning. We functionalize some new biomonomers. We obtain our polymers, formulate the polymers, apply and validate them into different sectors, in packaging sector and in textile sector. And in the second chemical route or coating development, we focus on the soil coatings for the cookware sector. All the work that we performed was, as I said, following all the steps considered in the safe and sustainable framework, and following all the value change in the different coatings and in the different application sectors. And I wanted to be fast, so that's the main points of Tornado project. Thank you.
I'll start following the order of the panel. I'll start with Dr. Picos. And actually, from, let's say, an industrial perspective, what do you think that there are main, let's say, key barriers to implement SSbD solutions in industry, and how, let's say, collaborative activities like IRIS would help them overcome this kind of barriers?
I think the speakers before me actually did a great job in saying what stops them and what they think are the barriers. And they concentrated on data, on training, the ability of people to do it. In other words, time. It's all of those. But what I have to say is, okay, Iris, initiatives like Iris do pave the way of overcoming those barriers, but it will take time. I think more important is to realize that each producing company does apply most of the principles within SSbD already, but it is not done, or in a lot of cases it is not done in the complete and systematic way that SSbD principles by the European Commission are required. So it's a matter of making this systematic approach practicable and applicable in an easy, transparent way so that industry can apply it without spending too much time, without having to have enormous teams, without having to spend a lot of money to train people and have people to apply it. So just as a conclusion, I suppose, to this question, it will take time, so we don't need to rush. We need to start thinking one level above, at a systemic level, rather than individual bits of action. And we need not fear the lack of data at the beginning. The lack of data is where LLMs and modeling and so on come in gradually to cover the gaps. Yes, with uncertainty. Yes, we'll have to deal with uncertainty like we've done in all of our lives and will do in the lives to come. And we have to make decisions in knowledge that we have a range of the parameters involved to deal with it. And as, of course, R&D progresses towards the final solution, this range narrows down into one single solution. One last remark is that the spiral that was shown earlier was very aptly depicted in the new framework, in that the process is not linear. And because of uncertainty, you may have to go backwards at times. You have to backtrack in one step or two steps in the R&D process before you go forward again into the more promising direction after you've known the exact or close to the exact values of the parameters you've assumed. So you assume something is white, but then towards the middle of the process, it turns out to be grey, and you have to backtrack again to go into that direction. So you have to be prepared to do that. And the challenge of the engineers and the chemists and the scientists and everybody else is to make that painless, to be able to do that before you've actually spent a fortune trying out alternatives. And this is where a lot of the effort will be put in the next few years, I feel. So the companies, the industry does not need to worry that a regulation will come tomorrow and they will have to comply. This is not the case. I feel that industry has to muster its voice in its totality and ask the Commission not to make anything compulsory until it is fully operable, until it is an actual realistic tool to apply, not to investigate, but to apply.
That also seems, let's say, a delay sometimes when we have follow-up process and once the PRL and we are preparing the industry in order to find the regulation.
Yeah.
Thank you. We can go next to Dr. Mirel Puma. And actually, a question could be what would be, let's say, the technical, also the data-related, let's say, challenges that would, let's say, slow down the implementation in the penetration of SSbD principles, let's say, and also in the PFAS-free, let's say, coding applications.
Okay. So the thing is that at the moment we are working at our medium technological readiness level, creating functionalizing additives or exploring new chemistry, creating new molecules. there is almost no data. Even if raw materials, you have a lot of available information on NASA, and when we are visualizing in chemical synthesis or getting into complex mixtures, it's more difficult. So modeling is work, but I'm not sure it's sufficient. At the moment, you're at almost step 2 and step 3 is the formulation application where we are dealing now is the coatings, PFAS-free coatings. You have formulation with many components potentially interacting themselves, and at the end, the final product that can release. We would like to avoid that there are any release to measure. So it's a lot of information, and it's an interactive approach because at the R&D scale, we will try many things before getting into the right performances. So data, yeah, I think it's a word that everybody is mentioning, that it's just something which is currently slowing down the process for the safety assessment, for the LCA also certainly, and especially when we are at laboratory scale, even having knowledge, even having available data on even at already industrial scale. I'm taking the example of biopolymers. Currently, even the data are available. It's not mass production. And so if you compare an LCA, fossil-based polymer, which synthesis is done in tons and tons of things, years and years, the LCA of the equivalent bio-based one will never be favorable. And so this is, it could give a very bad impression of the results, while in fact we are going in the right direction, but the scoring in the SSbD will not necessarily be as positive as we wish. I can speak along now.
Thank you. Professor Magani, so let's say based on your experience coordinating a motor project, which would be, let's say, the main SSbD principles that would be most challenging and difficult to personalize and go on with the surface in materials engineering, let's say?
I can do the example of the sector I'm referring to more than the others. As it will not be easy. We take time. Same. For instance, the industry is a very good industry, especially in consolidated sectors. Not so easy to change something, change the formulations, use for years, operations that typically be transferred from the father to the son. So, but there are some, let's say, aspects that we say push this transition. One is the end user requesting sustainability, sustainable processes in order to sell in a better way the products. And another law that I think is important to help this is circularity. You didn't mention it, was discussing other speeches here. Circularity will affect for sure also the paper industry. There is a fundamental need of they use the electrolyte, proven materials like the end products. So we are able to make sustainable these processes, not only economic. So larger view probably to be able to introduce all these aspects.
Thank you. Next one, regarding Dr. Say, one question would be, let's say, what to replace the PFAS based, let's say, material with SSbD based alternatives?
Thank you for the question. Yeah, I mean, from ProPlanet's perspective, the key barrier that we identified is performance. of the coatings that we developed. What do I mean by that? That's basically durability and the functional properties of the coatings. And I mean, for instance, anti-stick and the adherent properties of coatings. And the thing is that in comparison to the coatings that are currently used, so PFAS-based, the industry has a lot of experience with these coatings. They have a very long track record. And for the new coatings, even though we have very promising results in the project, we still don't know how long they will last and how well they will perform on long term. So in order to know that, you need a lot of time, also extensive testing, of course, and so on, to really say how long they can last. And this has, of course, like durability or reliability. That's an implication for the businesses. So if you have to think of replacing a piece to decode it more often, there's more maintenance, more spare parts, and so on, which has a direct economic impact as well. So I think that's why companies are still a bit cautious. Yeah.
Thank you. Dr. Ayona and Olego, one question, please, based on your experience also from NEOTEX and in general, how industries actually make use, how they react when they are looking to, they are using SSbD tools and methods and also models that would be associated in this field. How do they react?
Thank you for this question, Kostas. Well, first of all, I think that from the SSbD perspective, main tool, let's say, that is developed in the project is the model of decision support tool. It has 4 different models. So one is the materials information database. Then the model that would help to assess the environmental impact. Then another one for safety and regulation assessment. And finally, the machine learning and incident experiment. So all these models can operate independently, but also they are automated. So the interaction of our end users this support group was actually different. So, for example, the first one that is responsible for the validation of the energy demonstrator, they participated from the beginning in the creation of the material database, also in the construction of the decision support tool, but they did not interact with it directly because generally the idea was that the material will arrive to the validation step, to the high material level, will be already down selected from an initial pool of different materials. So the partner that actually interacted with decision support tool was the research and development center that was actually doing the work on the development and the preparation of the data materials. And then if we talk about the other end user that was responsible for the fabrication of the magnetic devices, they also interacted with several models of the decision support tool, mainly the one for the LCA assessment, and then the other one for the machine learning and design experiment. I also have to say that in between the tool and the user, there was also an SSbD expert, because it is not so mature yet. But I think that at the end of this interaction, the end user could optimize some of the supplier selection and also could solve some issues related to the optimization of the recycling processes and also transport of the materials. So I think that the most important is that in this project, we can see that the industrial partners are interested in these tools and are interested in contributing to the development of the knowledge because like they provide research and development.
So, Dr. Martins, one question could be, let's say, if you could identify any regulatory challenges related with the adoption, the national adoption, let's say, of SSbD solutions, and also including any kind of requirements related to worker safety.
So that question can be answered in several ways. So let's try to regarding the SSbD framework, it is actually pushing us towards the implementation of safe and sustainable principles in the early stages of the innovation process. However, the regulation translated. That's the problem. There's a big mismatch between these two pillars. On the other hand, the regulation is highly complex, and often quality, performance, and sustainability and safety regulation frameworks are not well aligned with each other. And it's very difficult for industry, in particular SMEs, to understand how they can integrate everything and how can they actually implement all of these regulations since the early stages of the development. Regarding the workers' exposure is another thing, is that health safety in companies or worker safety in companies is exclusively relying on harmonized operational limits, harmonized on regulatory orientations. And because of the new materials that are emerging, there are no occupational exposure limits defined. So companies don't know which reference values they should follow. So yes, in the end, I think the most important is the barrier for industry adoption of the SSbD and to move forward SSbD from concepts to its practical implementation is to align these two pillars and grant that safety, sustainability, performance are all together in these regulation frameworks and innovation support actions.
It may take more time to standardize and harmonize all these results, but maybe there is itself something. I don't know. Maybe that would be option. Thank you. Let's say that one question, as a recorded sense, comes from the industry, let's say from Group Gaza, and one key question challenge could be what are the big challenges? What are the difficult steps when you are going, when you are called to scale up and come from laboratory or pilot scale and you try to implement an SSbD-based solution into the real industry?
I think that the bottleneck of scalability from laboratory to industrial is a big gap between the laboratory development and production implementation. Many solutions, many chemistry work very well under control parameters in laboratory. But when you move to production, different variables come into play, like stability, contamination, different capacity of the tank, like volume of parts to treat. So it's very important in research and development and in the research and sustainability-based design approach to consider all these parameters to guarantee the lifetime and performance of the solution and the final coating. Another aspect very important is the sector where you work. Because
sector lines like automotive or aerospace, when you change chemical in the process, need to do a validation. The final client want to do lots of tests to validate the process and the final coating. So for me, this is a challenge for the company and be a barrier to implement the research and development.
Thank you. And let's say closing this day panel with one question that is not about, let's say, today, it's about future. Let's say, taking advantage of your experience in the NATO project and any key lessons coming from this project, which would be, let's say, the main insights, the main, let's say, guidelines where we should focus in the future, let's say, SSbD associated based related projects, let's say.
So, in Tornado, the first problem that we found between the, let's say, SSbD, the partners and the technical partners was the language that we found. So that's the key point. All of us we talk the same and understand also what the sustainable part means from the technical. That also was the key point. Another key aspect is the impact. In this project that they have, let's say, low TRL, it's difficult to for the SSbD partners or to develop a complete guideline for the SSbD framework to get all the data that we need, because we've been working at large scale, and when we increase the TRL to the pilot scale was not high enough for them to have the proper data for a complete guideline. And another important issue also is that, well, I think that the technical part is not going to be data as easy, because each of the companies has their own properties or their own IP property. And this is very, very difficult to establish. So I think that these are some problems that we are going to find in order to have, let's say, a guideline or free information to have all the data that we need for the guideline.
Thank you. Thank you. I believe that maybe I would like not to spend only 1 minute, but should be 15 minutes. Just for one quick question, because we have to be also fair with the audience who was here so much time. So if we can have, there's a question, maybe one question, time for one question from the audience. Otherwise, the questions were very good already.
So there is a question. Sorry. Well, before just say that there is a lunch outside for all the participants of the SSbD workshop.
So the question is, who doesn't want to lunch?
We can actually be asked during lunch, but anyway, we do clear the room by 1:25, but you can have a question.
Thank you very much. Really a wonderful constellation of very bright projects. I would like to very quickly ask, do you cooperate with each other? Do you exchange data? Do you exchange experience? Do you, are you planning a bigger impact as a group rather than as individual projects? I mean, you can perfectly come to Paris and present all this work to SSbD.
Yes, so if you have speakers who wants to take a speaker. You can contribute.
Benefits do happen. Lots of the organizations, lots of the companies participate in more than one project in any case. But communities and hubs like the Iris Hub, the ENC Hub, etc., do provide spaces for that sort of free exchange of information. proprietary information is difficult to clear, of course, as we said before. There are mechanisms for similar things like the REACH mechanism of sharing data, but this has not come about for SSbD yet because SSbD is not a regulation. So it's less obligatory. But it's now the time where, with these plethora of projects having been funded by the EU, for these projects to come together and start talking more about themselves, individual sector and application does become more relevant in sharing the barriers, the thinking, the difficulties. And me being part of the IRIS community, I have seen propositions by other projects coming in and asking for views on findings they have had. And so this is kind of the platform in which one can do this. So that I don't know.
Yeah, well, maybe just a few words first. I'm really happy to say that this is called the Talent Project in the same that was run under the same role. So we are forcing cluster together with WhatsApp and the next 3D project also involved, but that one was already finished. So we, from the beginning, established several joint communication simulation actions. So we had cluster meetings where the experts could exchange their opinion or share the challenges that they face. We also have shared simulation channels, for example, cross promotion and the LinkedIn, and other social channels. Also contribute to the newsletters of each other and try to organize conferences because in the end we have many similarities in the projects, even though the topics are different. And of course, confidential information should remain confidential, but that's not the barrier for not collaborating. And I know for maybe
well, there are several classroom activities and mobile projects. Most of the time, you will have more than 1 or 2 or 3 projects are under the same one. Okay, so we have to close this panel, and we're going to our next steps. This is the last you said already.